Here is another optimization problem. The story is a lifeguard is patrolling a beach. This is a body of water like an ocean. And he's at this point on the beach and he spots a swimmer in distress who might be drowning. And he has to rescue the swimmer in the shortest amount of time. So he has an option here. He can run along the shore first and then enter the water at some point and then start swimming to rescue the swimmer. The reason he would want to run along the shore first is because his running speed is much faster than his swimming speed. So the idea here then is to minimize the time that the lifeguard takes to reach the swimmer by figuring out where he should enter the water along the shore. We have parameters on the problem. The distance that the swimmer is from the shore is a capital L. And then if we draw the straight line to the shore, the distance from the shore to the lifeguard is a capital D. Two other parameters, the running speed of the lifeguard is little r, and the swimming speed of the lifeguard is little s. And we know that the swimming speed is less than the running speed. So we need to introduce unknowns into this problem that we want to solve for. I choose to let this distance here to be x, and then the distance that the lifeguard needs to run along the shore would be d minus x. That makes the algebra a little bit easier. So the distance the lifeguard runs is d minus x. We also need the distance the lifeguard swims. That's the hypotenuse of this right triangle. So that's the square root of x squared plus L squared. Okay, so how do we calculate the time that the lifeguard takes to reach the swimmer? We need to use an elementary physics equation. So the time is equal to the distance divided by the velocity. You may remember that velocity times time is distance. So that's just a solution for time. Okay, so let's compute the total time that it takes the lifeguard to reach the swimmer. I'll call that capital T. So capital T is the time spent running. So the lifeguard runs a distance d minus x with running speed r. So that's d minus x divided by r, plus the time spent swimming. So the distance swum is root x squared plus L squared, and then we divide by s. So plus root x squared plus L squared divided by s. And that's the total time then spent by the lifeguard. We want to minimize the total time with respect to our variable x. When I say the phrase minimize, your eyes should pop out and you should think, oh, I know how to do that. I've learned the calculus. I take the derivative of t with respect to x and set it equal to 0. So let's take the derivative of t here. We have the derivative of t with respect to x. So the derivative of the first term is very easy. That's just negative 1 over r. And then the derivative of the second term is using both the power rule and the chain rule. So this is x squared plus L squared to the 1/2 power. So the derivative brings down the 1/2. Then we have x squared plus L squared to the minus 1/2 power. And then the derivative of the inside is 2x. So the 2's cancel. And you can see, if you can't do this in your head, then stop the video and use a piece of paper. We would get s divided by the square root of x squared plus L squared. And then dt dx, we set it equal to 0 to find the minimum of t, the minimum time. So this is an equation. We can write that as x over s root x squared plus L squared is equal to 1 over R. Okay, an equation for x. From here on, it's algebra. How would I solve this equation? I don't like the square root, so I would square both sides of this equation. Then I would cross multiply, and we would have then x squared on both sides of the equation. And then I would put all the x squareds on the left, everything else on the right. I would isolate x squared, and then I would take the square root. Okay, you can do that. If you need to do that, if you want to do that on a piece of paper, go ahead. So finally, I would want to have some physics here. The swimming speed is less than the running speed. S is less than R. So I would like to write the resulting expression in terms of S divided by R. So if I do that and solve for X, we would get X is equal to S over R times L divided by the square root of 1 minus S over R squared. And that would be our X here. So the distance that the lifeguard has to run is D minus X. So let's help the lifeguard. The lifeguard is not going to calculate square roots in his head before he starts trying to rescue the swimmer. So let's give what's called a heuristic to the lifeguard. Let's give the lifeguard a rule of thumb here. So if you're a good swimmer, then you usually run 4 times as fast as you can swim. So this S over R is about a quarter. Lifeguards are good swimmers. If S over R is a quarter, then S over R squared is 1 over 16, and 1 minus 1 over 16 is 15 over 16. It's a number close to 1. So this denominator in terms of helping the lifeguard is about 1. So he doesn't have to compute square roots. So this X then is approximately 1/4 L. So that the distance that the lifeguard has to run, our D minus X, is about D minus 1/4 L. So the lifeguard has to run the distance, not quite D, but the distance D subtracted from that 1/4 of the distance of the swimmer from the shore. So the lifeguard looks where the swimmer is and then runs a distance so that he still has about 1/4 of this distance left before he enters the water. Maybe a useful heuristic for the lifeguard. Does it make sense? Right, if the swimmer was very close to the shore, then L would be small, and the lifeguard would basically run almost all the way on the shore. On the other hand, if the swimmer is very far from the shore, then the lifeguard should enter the water at a sooner point. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video.